Hello, everyone. First of all, it's great that more sustainable enthusiasts are coming to OCP events more and more. So my name is Yilmaz, my colleague Johan Kristiansson. Today we want to discuss about the sustainability innovations when it comes to distributed computing paradigm. So as you can see in the image, we are coming from Sweden up from Research Institutes of Sweden. Our office is located at Luleå, which is up north in the Sweden, which is a great environment actually when it comes to data centers. If I'm not mistaken, more than 360 days of a year, external temperatures, they are not exceeding 24 to 25 degrees. So it's a paradise. So what happens if we need to, today we will discuss more what happens if we need to take these data centers and compute elements into somewhere, take them out of their comfort zone into somewhere which they are not going to appreciate that much. So two EU-funded, publicly funded projects we are going to discuss, introduce today. One of them is Heatwise, the other one is Sovereign Edge Cognite project. Interestingly, starting from Heatwise, this is not a data center project. This is a project focusing on the climate neutrality of the buildings. So the specific challenge about this project was, this project was targeting buildings with intensive IT loads. So we will discuss more like how we are trying to tackle this issue with buildings with high IT load, and we consider it as a microgrid or grid integration problem for the data centers, and we will discuss how digital twins can actually help us to maximize the efficiency. We will introduce AI workload orchestration, which is being developed under the Cognite project. Then finally, my colleague will be introducing RISE's open source Colony OS mate operating system, and we will discuss how we can actually utilize it in distributed computing. So, everything is smart nowadays, right? Your fridge, your car. My car has an API, for God's sake. How we could foresee it in 20 years before? So in this world that you can see on the left-hand side, we actually generate more data than we can handle in the traditional way. And this is not the only challenge. Most of the applications that we encounter nowadays, like smart factories, augmented reality, and maybe smart cars of the future, they require lower latency. So what we do, we have to actually change, we have to experience a paradigm shift. We have to carry the computational sources closer to the end users, and this is where the challenge begins. This is a big risk where Border Step Institute actually identified it quite well. We have different scenarios in front of us. Just giving an example, within the European Union, in 2018, the overall data centers energy consumption was 26.8 terawatt hour. So in a good scenario in the future, if everything goes as we planned, hopefully, fingers crossed, the energy consumption of the data centers are going to go down, which is represented with the green line in the graph. But in the worst case scenario, we can go actually up higher, which would be the worst scenario. But what I want to highlight here, I don't know if you see it good, but the brown line is actually the consumption statistics, which is being represented with the edge computing and distributed computed inclusion into this equation. So how we can actually mitigate this risk we are experiencing right now, as discussed, if we are getting out of our comfort zone, we have to be better integrated into the energy grid that we are going to collaborate with. So we have multiple factors that we consider during our studies. One of them is obviously our workload that we want to optimize and we want to track and we want to maintain our uptime. Obviously, energy pricing and carbon density of the grids that we are integrated into. Renewable energy, of course, if possible, this is a great enhancement, another factor that we consider. But especially in the Heatwise project, we consider the heat demand. So how it works in this case, for us, it is, if we are talking about buildings, and it is the first project of mine, we are mostly focused on the building, so this is a new chapter of my life. So this is a demand matching problem for starters. So I will step by step go and try to explain how we want to overcome this demand matching problem. So main idea is replacing the boilers of the buildings. I mean, you probably heard about it many times in OCP events. But there is one fact. According to Eurostat, around 80% of the energy consumed in the households are related to water heating and space heating. 80% of this. That's why this statistics explains the importance of why it is important that we actually recapture the waste heat and we actually utilize it in the community. So one of the things we consider, the micro scale consideration of us is having some high return temperatures. One important fact, as long as you are not transferring the waste heat, maybe you might not need high return temperatures like 70, 75 degrees. If you utilize the waste heat in the building, actually most of the buildings need around 50 degrees. For space heating. So we adapted, actually one of the partners of this project is Zutacor. So we adapted their two-phase pool boiling direct-to-chip cooling system to maximize the return temperatures. And we are also really keen on increasing the return temperatures by also ensuring the safety of silicon. We conduct some computational fluid dynamics and thermal analysis with DSTech, another partner of this project. So in this micro-scale optimization strategy, we actually maintain the best return temperatures while optimizing the IT systems. But in the big picture, when we see the big picture in the macro scale, we need to actually really understand what's happening. So actually creating a replica of a real-life environment, a grid, would help. So what we want to do, we want to observe the energy transitions in between different components of a grid. So what are they? Let's go through it. First of all, energy users, which are responsible with the heating, like domestic hot water and ventilation. So in normal cases, we actually supply this heat maybe from district heating, from a boiler, which we want to reduce now, and hopefully in the future it will be mostly recovered heat. So we also have other components. We have cooling systems and heat pumps. Again, we would prefer to recapture good return temperatures, not to go for cooling systems or heat pumps. That would be the most sufficient case. And another factor that we want to observe and also predict in the future is our dependencies of the grid. So just consider a case, as long as we know how the external temperatures are going to change, how the weather is going to change, how much renewable you can generate, and how external temperatures are going to affect your power consumption, especially related to cooling, then the image is going to be a bit more clear, how you should actually optimize the building's energy. So if you predict the big picture, this is the main aim of us, then we can actually easier optimize the operations in the data center or any kind of IT infrastructure. So this actually requires a special skill set. So I will leave the stage to my colleague Johan. He will explain how he's orchestrating the workload.
So yeah, hi, my name is Johan Kristiansson, also working at RISE. So in order to harness energy waste and meet energy demand, workload needs to be managed dynamically. So I will talk about two different projects that we're working on. And the first one is called Cognit, and it's about developing a function as a service, serverless computing platform for our edge to cloud continuum. So an important part of this framework is an AI-powered orchestrator. And the purpose of this AI orchestrator is to scale the platform horizontally and vertically, but also decide where the different clusters should be deployed. So now I lost my word a little bit. What was I about to say? So what you can do with the AI orchestrator is that you can, for example, you can implement carbon-aware scheduling. So you can, for example, if you can defer workloads in periods of time where the carbon intensity is lower, or you can also scale them. You can also do geographical optimizations. So you can, for example, strategically assign workloads to regions, geographical regions where the carbon intensity is lower. And you can also use this to connect to the digital twin that Áaƒüatay mentions. So we can schedule workloads to actually meet the workload of buildings. So let's switch to the other slide. So I can also mention that we are in the Cognite, we are working with different use cases, 4 different use cases, and you can see the partners. We are OpenNebula and SUSE is part of this project. So I also now want to talk about this cloud edge continuum. You might hear about everyone talking about continuum. What is it? And a continuum is a collection of computational resources that are managed in a unified way. So if you have a continuum, you can, for example, run workload anywhere in the continuum on different platforms. So that's one of the benefits. And then you can optimize resource utilization, energy efficiency, or network latency, for example. So now I'm going to show some animation here. So instead of interacting with directly with different platforms, you would interact with this meta operating system. And the meta operating system is a kind of a one way to implement a continuum. So this platform has API it would be very similar to an operating system from an API point of view. And this is a kind of a broker-based architecture. So you have executors that are middlewares that connects to different platforms. So we have integrated this with your HPC systems, and you can also then, for example, plug in a Kubernetes running in a public cloud. And of course, you can also use like on-prem and edge. And this also works with IoT. So this is what I mean. You have a collection of different interfaces that are unified. Then if we, so you can, of course, you can remove platform dynamically. If you don't want a supercomputer, you can just remove it. So let's focus on a public cloud and the edge that can be located in different buildings then. So what we can do with this, we can integrate the AI orchestrator that we developed in the Cognite project into this meta operating system, and we can also connect the digital twin from the Hitwise project into the AI orchestrator, and then this enables this very flexible architecture where you can schedule workloads to meet peak demand in buildings. So as a conclusion, we have 3 building blocks. We have a digital twin that it collects real-time data and make predictive insights about electricity and energy transmissions. And we have the AI-powered orchestrator that it can optimize sustainability and energy usage in this continuum. And then we have a meta operating system that ties everything together in one single platform. So that's it.
Thank you. So yes. I think it is time for call to action. I think we should start with acknowledging that we should do better when it comes to wasted valorization. And we have to also scale this up, like starting from smaller systems to hyperscalers. We should distribute it, and it should be a wasted market. That people actually really can integrate. So even for such a system, we believe that using a replica, a digital replica of an existing system can be quite helpful for the future. So the other thing is replacing the boilers. I think I will keep on repeating this. This is one of the things that we would have enormous savings. We are not talking about how to optimize general efficiency, but we are actually cutting down a main energy spending in the buildings. And also, obviously, both projects are still going on, Heatwise and Sovereign Cognite projects. We strongly recommend you to go to these QR codes and follow up our pages to keep updated about the progresses within this project. And as always, I strongly recommend you to follow EU Code of Conduct Data Centers Energy Efficiency to actually be more aware of the efficiency practices that you can implement in your systems. I think, yeah, we have some time for questions. This is the whole presentation. We would like to answer some questions. Okay, then. Thanks a lot.
Thank you.